There are these massive industrial vessels all around us, in chemical plants, refineries, factories, and they're holding back just immense forces. But what if there's a tiny invisible flaw, something smaller than a human hair, just starting to grow deep inside? Well, the results could be absolutely catastrophic. And that sets us up for a pretty high stakes industrial mystery. So, yeah, how do you find a failure before it actually happens? Especially when you can't see any warning signs at all. I mean, this is the central challenge, right? The big question for engineers trying to keep these silent giants safe. The integrity of an entire facility and the safety of, well, everyone around them depends on figuring this out. Okay, so take a look at this. A lot of these vessels are made from something called fiber reinforced plastic, or FRP. And this stuff is super strong, it doesn't corrode, it's great. But under all that constant stress, from pressure and temperature swings, it can start to develop this really sneaky internal damage. We're talking about things happening on a microscopic level. Fibers breaking, tiny cracks, stuff you absolutely cannot see. But these little flaws can grow and grow until, well, sudden failure. You listen. Seriously, that's the answer. The way you find a crack you can't see is to listen for it. Now, obviously not with your own ears. We're talking about technology that is so sensitive it can literally hear a material breaking apart at the microscopic level. All right, let's get into it. This whole thing is called acoustic emission testing, or just AE. And it's what's known as a non-destructive test, which means we can check on the health of the entire structure in real time just by listening for these super high-frequency sounds that it makes when it's under stress. The best way to think about it is like a stethoscope, but for a giant industrial tank. Seriously. Every single time a tiny little fiber inside the material snaps, or a microscopic crack gets just a little bit bigger, it releases this tiny burst of energy. It's like a ping, a sound wave that's way, way too high for human ears to pick up. But AE testing uses these super sensitive microphones to hear those screams. And what's amazing is it doesn't just tell us that damage is happening, it can pinpoint exactly where. But it's not as simple as just slapping some sensors on and hitting record. No way. To get data you can actually trust, you have to prepare the whole scene first. The main goal here is to make sure that the only voices you end up hearing are the ones that signal fresh and potentially very dangerous activity. And that brings us to a really crucial first step called conditioning. So before the test even starts, you actually reduce the pressure in the vessel and you just let it sit there for a while. And how long depends on its normal workload. So for instance, if a vessel usually operates at, say, 60% of its max pressure, it needs to rest at a lower pressure for 5 full days. What this does is it basically quiets down all the old, stable flaws that aren't a problem. That way, when we do start the test, any sounds we hear are almost certainly coming from new damage that's actively growing. Okay, so the vessel is prepped, it's quiet. Now what? How do we actually listen in? Well, this is where the high-tech ears come into play. We're talking about a really sophisticated system of sensors and processors, all designed to catch every single tiny whisper of distress. And what's so cool about this is how the whole system works just like a nervous system for the structure. The sensors, those are like the sensitive nerve endings, the ears, right? They turn the sound waves into little electrical signals. Then you've got the preamplifiers. They're like the nerves, boosting those super faint signals so they can travel. And all of that information feeds right into the processor. That's the brain of the whole operation, analyzing everything in real time to figure out where the sound came from and, how serious it is. And you can't just stick these sensors anywhere. Oh no, it is a precise science. You see here, for both vertical and horizontal tanks, engineers place them very strategically, right near the spots that take the most stress. We're talking about nozzles, manways, and these knuckle regions where the different parts of the tank join together. And because the brain, the processor, knows the exact location of every single sensor and it knows the speed of sound through that specific material, it can triangulate the source of any scream with incredible accuracy. All right, the vessel is prepped, the ears are in place, now we get to the heart of the investigation. It is time to start carefully applying pressure. We're basically going to interrogate the structure and make it talk. And you don't just crank the pressure up to max all at once. That would be a bad idea. No, the whole process is very methodical. You increase the pressure in steps. So you'll go up to maybe 40%, then pause, then up to 60% and pause. Each time you pause, it's called a hold period, and it lasts for a few minutes. And it's during these holds, that's when the engineers are listening with everything they've got. So you see the rhythm here? Increase the stress, hold, listen. Increase, hold, listen. Now, a healthy, happy vessel should get pretty quiet during those holds. But a vessel with a growing flaw, it'll often keep making noise. It just keeps screaming, even when the pressure isn't increasing. And that step-by-step process is what lets us hear that absolutely critical difference. Okay, so the test is done, the vessel has talked, and now we have just a mountain of data. And this is where the real detective work begins. Engineers now have to comb through all of it, looking for those telltale acoustic signatures, the signs of a structure that's in trouble. So what are they looking for exactly? Well, it boils down to a few key things. Think about it like this. A healthy vessel, it's pretty quiet during those holds. A damaged one? It keeps making noise, continuous emissions. A damaged vessel might also start screaming at really low pressures. And probably the most important clue of all, it's going to have a low felicity ratio. Now, this felicity ratio thing is a brilliant piece of evidence. It's actually a pretty simple concept. A material shouldn't make any noise until you stress it more than you've ever stressed it before. So let's say we take a vessel up to 80% pressure, then we back off. The next time we increase the pressure, it should be totally silent until we get past 80%. Make sense? But what if it starts making noise at like 70% the second time? That is a huge red flag. It tells you that the first pressure cycle actually damaged the material. It made it weaker. That's what a low felicity ratio means, and it is a major indicator of a serious problem. So, after looking at all the acoustic clues, the noise during the holds, the total number of screams, and that all-important felicity ratio, it's time. Time to deliver the verdict. Is this vessel safe, or is it a ticking time bomb? And this isn't some gut feeling, right? It is a super rigorous, data-driven process. It's all laid out in a flowchart, kind of like this one. At every single stage, the data gets compared against these really strict criteria. For example, one of the big questions is, did the noise during the hold period go over the limit? If the answer's no, you keep going. But if it's yes, boom, the test stops immediately and that flaw gets evaluated. It's just a clear, logical path that leads straight to the final verdict. So in the end, it all comes down to one of three outcomes. The best case, obviously, is a pass. The vessel is safe, good to go. The next one is evaluate. That means the AE test heard something suspicious and it needs a closer look, maybe with something like an ultrasound. And then there's the worst case, reject. That means a critical flaw was definitely found, and that vessel has to be taken out of service right now. The whole point of all of this is to find that flaw before it has a chance to fail. So when you think about it, this technology gives us this incredible ability to hear the invisible weaknesses in things, to hear the stress before it turns into a disaster. And that kind of makes you wonder, doesn't it? As we build more and more complex systems, not just in engineering, but in technology and our society, what other invisible stresses should we be learning how to listen for?